Introduction. The ubiquitous quantum realm. The document begins by establishing the central premise that the quantum realm is not a separate, exotic place, but rather the fundamental reality underlying everything we experience. As the text states, you're already in the quantum realm. Everything is quantum from bottom to top. However, quantum effects are often subtle and overshadowed by the more intuitive rules of classical physics in our everyday lives. 2. Classical physics. A useful approximation. The briefing outlines classical physics, primarily represented by Newton's laws, as a set of intuitive rules that describe how objects behave at macroscopic scales. These rules include the idea that objects have defined positions, do not spontaneously jump, and have predictable responses to forces. The text emphasizes that while Newton's laws are expressed with precise mathematical language, they are ultimately approximations, not the full truth of reality. They serve as practical guidelines for our everyday experiences, but fail to capture the deeper complexities of the universe at the smallest scales. 2. Quantum mechanics. Unveiling the deeper reality. Quantum mechanics is presented as the more fundamental theory that governs the base code of the universe, lying beneath the approximations of classical physics. The document highlights the stranger reality revealed by quantum mechanics through several key concepts. Quantization. Properties like spin occur in discrete, irreducible amounts rather than continuous values. The analogy of a spinning basketball illustrates this. Slowest spin is 1 turn per 256 trillion years. Next is 2 turns. Similarly, electrons have intrinsic angular momentum that is quantized. Weird properties. The briefing introduces 3 key counterintuitive quantum phenomena: superposition, the ability of a quantum object to exist in multiple states simultaneously. As stated, an object can be entanglement, a phenomenon where 2 or more quantum objects become linked in such a way that they share a combined reality, regardless of the distance separating them, meaning neither independently real. Quantum leaping, the ability of objects to pass through energy barriers, appearing on the other side. V. Quantum computing, harnessing quantum strangeness. The document then transitions to the field of quantum computing, which aims to leverage the strange properties of quantum mechanics, superposition, entanglement, and quantum leaping to achieve unprecedented power for specific computational tasks. The text clarifies that quantum computers are not intended as replacements for general-purpose classical computers, but are rather designed for problems like simulating large quantum systems. The field is described as being in an experimental stage, focused on building basic functional components rather than fully developed systems, but it is characterized as a big dream with a clear development path. V. Bits versus qubits. The fundamental units of information. A key distinction is made between classical bits and quantum bits. Classical bits store information as binary states, either 0 or 1, analogous to a light switch on-off or a magnetic domain up-down. These bits are processed by transistors on classical computer chips. Quantum bits possess the ability to be 0, 1, or a superposition of both simultaneously. Furthermore, qubits can become entangled across multiple qubits, exponentially increasing computing power. The goal is to engineer systems with hundreds, thousands of entangled qubits to surpass classical computers. VI. Engineering qubits, challenges and solutions. The briefing details the challenges and engineering approaches involved in creating practical qubits. Challenges with atoms. While single atoms can serve as qubits, difficulties arise in achieving atom-to-atom communication and the lack of customizability of atomic properties. Superconducting circuits. These are presented as a promising alternative, emulating atomic behavior using customizable electronic circuits. A crucial requirement is cooling metals to superconducting states. Superconductivity, this phenomenon, where metals conduct electricity with no loss due to electrons moving in lockstep, forming a macroscopic quantum state, is essential for creating stable and controllable qubits. Superconductivity allows circuits to behave like one giant electron, tangible at a macroscopic level. And inductors, forming an LC oscillator, is explained. Achieving quantum access requires suppressing noise by cooling to superconducting temperatures, revealing discrete energy levels. Unlike natural atoms, these systems are customizable. V. Controlling qubits, precision microwave pulses, and nonlinearity. Controlling the state of qubits relies on precise manipulation, microwave pulses. Operations are performed using microwave pulses at specific resonant frequencies. For example, a precise frequency pulse is needed for a 0 to 1 transition. Nonlinear inductors. Linear energy levels can cause control issues due to overlapping frequencies. Nonlinear inductors are crucial for creating unique frequency spacings for each transition. Josephson junctions. The magic. These are described as key components with a layered structure of superconducting metal, thin oxide insulator, another superconducting layer. Their function relies on quantum tunneling, where electrons leap through the thin insulator. They provide the necessary nonlinearity amplitude changes frequency, which allows for precise control using unique microwave pulses to switch states or create superpositions on logical gates. 8. Challenges in quantum computing, noise, cooling, and signal processing. The briefing outlines significant challenges in the development of quantum computers. Noise and decoherence. Discrepancies between theory and hardware lead to external noise disrupting qubits. Decoherence, where the environment alters fragile quantum states, introduces errors. Cooling systems. Maintaining the extremely low temperatures required for superconductivity necessitates giant refrigerators that isolate qubits at around 10 millikelvin. These systems employ multiple cooling stages, vacuum insulation, skinny cables, and magnetic shields to protect the delicate quantum states. Signal processing. Managing signals entering and leaving the cryogenic environment is complex. Input signals travel through cooled stages to interact with qubits, while output signals are amplified via quantum-limited amplifiers and isolators. Dispersive readout. The state of a qubit is often measured indirectly using dispersive readout, where a cavity around the qubit shifts frequency slightly depending on the qubit's state. This shift is detected through phase shifts in microwave signals. 8. Challenges in quantum computing, noise, cooling, and signal processing. The briefing outlines significant challenges in the development of quantum computers. Noise and decoherence. Discrepancies between theory and hardware lead to external noise disrupting qubits. Decoherence, where the environment alters fragile quantum states, introduces errors. Cooling systems. Maintaining the extremely low temperatures required for superconductivity necessitates giant refrigerators that isolate qubits at around 10 millikelvin. These systems employ multiple cooling stages, vacuum insulation, skinny cables, and magnetic shields to protect the delicate quantum states. Signal processing. Managing signals entering and leaving the cryogenic environment is complex. Input signals travel through cooled stages to interact with qubits, while output signals are amplified via quantum-limited amplifiers and isolators. Dispersive readout. The state of a qubit is often measured indirectly using dispersive readout, where a cavity around the qubit shifts frequency slightly depending on the qubit's state. This shift is detected through phase shifts in microwave signals. X. Tools and experiments. The iterative nature of research. The development of quantum computing relies heavily on advanced experimental tools and an iterative scientific process. Vector Network Analyzer. This instrument measures signal amplitude and phase across frequencies and is used to test critical components like cavities before cooling to ensure functionality. Iterative science. Progress is driven by constant experimentation. Test devices. Gather data, swap for new designs. This requires advanced tools, skilled users, and creative scientists. X. Role of national laboratories. Fostering long-term innovation, national laboratories play a crucial role in advancing quantum computing due to their long-term commitment. They are equipped to tackle big, slow problems like next-gen computing. Expertise. Their existing expertise in fields like lasers, superconductors accelerates innovation. Openness. Their openness to new ideas and iterations drives progress in quantum tech. 11. Conclusion. Embracing the quantum reality. The document concludes by reiterating that the quantum realm isn't fiction or separate. We've always lived in it, our understanding and ability to harness its principles through science and engineering represent an awakening to its implications. The document also points to the Science and Technology Review as a resource for further information on quantum experiments.